Okay, one of the most commonly seen and discussed noise sources in electronic circuits and in general is what we call the thermal noise or Johnson noise. Now, the thermal noise is caused by random fluctuations, the thermal random fluctuations of the charge carriers. We talked about this extensively a while back when we were talking about device physics, right? We're saying that these things are moving, electrons are moving very rapidly because they're very lightweight. So basically, a little bit of energy can make them go around a lot. And we saw that because of the Equipartition theorem, which basically stated that in thermal equilibrium, each degree of freedom, classically for classic particles, when the energy of the photon, basically, the photon energy is much larger than the kT. Photon energy is, yes, larger than kT. What happens that in classic particles, when you are subject to Boltzmann distribution, each degree of freedom takes 1/2 kT of energy. And we saw that because of the fact that the electrons were light, the electrons are moving very rapidly, but electrons are also charged, right? So this random thermal movement induces electric field fluctuations. And these fluctuations in electric field basically translate to noise. So we'll do a derivation of the Nyquist noise. We will see how it behaves, or the shot noise. Sorry, we do the derivation of the thermal noise or Johnson noise in the system. Now, but before we do that, let's briefly talk about a theorem that's important because it's important to understand the source of noise. This theorem comes from physics also. It's called fluctuation-dissipation theorem. So fluctuation-dissipation theorem essentially states that if you're in thermal equilibrium, anything that generates noise has to have loss. And anything that has energy loss has to generate thermal noise. One way to think about it is that, if you have a noise source, if you have a resistor that's generating noise, this noise is coming from somewhere, right? Where is the energy coming? Where is this energy of this noise coming if you have, let's say, a resistor that's generating noise for you? Well, this resistor is in thermal equilibrium with some sort of a reservoir, right? And the energy is basically coming out of the reservoir and going into your system. So if it was constantly absorbing and extracting energy out of a thermal, a reservoir, then you're going against the second law of thermodynamics. So which basically means that it needs to be able to absorb the same amount of energy the other way and needs to go back to the reservoir. So it means that you get thermal noise whenever there is dissipation. So fluctuations and dissipation go hand in hand, and they're proportional. So if you wanted to determine what kind of components generate thermal noise and what components do not, look at which components have energy loss and which components don't. So for example, a regular resistor would generate thermal noise because it has loss. If you put energy into it, it will dissipate it. It turns it into heat, right? A capacitor, an ideal capacitor, on the other hand, does not dissipate energy, right? Doesn't turn it into heat if it's an ideal capacitor. It stores energy, but it doesn't dissipate. Therefore, it does not generate thermal noise. So this is really the metric, the way to tell if something generates thermal noise or not. So if we think about it from a very simple perspective. But now, so let's try to calculate what the properties of this thermal noise are from some thermodynamic arguments, right? So we'll start with simple thermodynamics, and then we'll expand it and discuss it. So let's assume that first you have two resistors. Resistor R1 attached to resistor R2. So they're put in parallel. So they're attached to each other. And let's say we know that each one of them generates some sort of a voltage source, right? So we call this V1N and V2N. That's coming, and each one of them is in thermal equilibrium. Let's say both of them initially, let's say they're at the same temperature. Let's say both kept at the same temperature. They're in thermal equilibrium with their reservoir. So in this case, of course, resistor 1 generates some noise, and resistor 2 generates some noise, and then they will do energy exchange because because they're electrically connected, there would be some power going from left to right. Let's call this P12, and there would be some power going from right to left. This one is really So going from right to left, let's call it P21. Right? So now you have these two resistors, and then they are exchanging heat. Now, if they're both at the same temperature, what can you say about the relationship between P12 and P21 if they're at the same temperature? They have to be the same, right? Because otherwise, you're extracting energy, you're extracting work from two reservoirs that are at the same temperature. And you'll be violating the second law of thermodynamics. So they have to be the same. Now let's calculate what these things have to be. So let's say if you will use, for doing that, we'll use superposition, right? So these are linear circuits, you can use superposition. So let's say, what is the power delivered from this noise source 1 to noise source 2? Let's call it Vn1 actually, and Vn2. So Vn1 to R2, what is the power delivered? Well, you know, the voltage that is generated here, if you're using superposition, we are nulling this thing, so this becomes a short circuit, right? So the voltage across here is the voltage resistive divider, right? Simply it's R2 divided by R1 plus R2 times V1, or Vn1, is V2, the voltage across the resistor 2. So what is the power delivered to it? The power delivered to R2 is this squared, so the power P12 is V2 squared, or let's say Vn2 squared, divided by R2, right? That's the power delivered to R2. It's voltage squared, or sorry, V2 squared divided by R2. The voltage across itself squared divided by the resistor, which is this quantity. So this becomes Vn1 squared times R2 squared divided by R1 plus R2 squared. So one of these cancels, so that's the power delivered from P12. And by similar argument, you can say P21 is basically Vn2 squared R1 over R1 plus R2 squared. Now, if they are at the same temperature, we argued that if, let's say T1 equals T2, let's call this T2. If T1 is equal to T2, then we know that P12 is equal to P21 by second law. Now, if P12 and P21 are equal, then what happens? What can you say? If you look at these expressions, it's pretty straightforward. We can equate them, right? We can say Vn1 squared from the first expression, R2, not R2 squared, divided by R1 plus R2 squared has to be equal to Vn2 squared R1 over R1 plus R2 squared. So these guys cancel, obviously. And what do you get? You get Vn1 squared over R1 equals Vn2 squared over R2, which imply that Vn squared should be proportional to the value of the resistor. So we have already determined one thing about the properties of this voltage noise source, that it should be proportional to the R, to the resistor. So the voltage source in series, the power of this voltage source, the voltage power spectral density, is going to have to be proportional to R, the resistor, right? So that's one thing we know. Now let's take another step. Now let's assume that T1 is not equal to T2. Let's say T1 is not equal to T2. Let's say there are two different temperatures. If you assume that there are two different temperatures, then what happens? Well, obviously there will be net heat transfer, right? There can be, because one of them is hotter than the other one. So, and the net heat transfer has to be proportional. So the ratio of the power transfer, the delta P, has to be proportional to delta T, the difference in the temperatures. In other words, P12 minus P21 has to be proportional to T1 minus T2. Does this make sense? It says the larger the difference between the temperature is, the more energy, the net energy is being transferred between one and the other. Right? So if this proportionality holds for all temperatures, it should hold for one of these temperatures being actually 0 Kelvin. Right? So it should be valid if T2 is 0 Kelvin, absolute 0. And if you set it to absolute 0, then what do you get? Then you get P12 is proportional to T1. Now, why do we set P21 to 0? Because at absolute 0, there is no energy available to be transferred out, at least classically. Right? So from that perspective, we basically say that then, therefore, P12 is proportional to T1. But we also know one more thing, that V12, right? Oh, I'm sorry, Vn1 squared is also proportional to P12, which basically means that Vn squared, the power spectrum, also has to be proportional to T. So now we know that the energy, the noise power of this thing has to be is proportional to the resistor, and it's also proportional to the temperature, the absolute temperature. Now, we don't know what the proportionality constant is. We haven't found anything on that front, and we'll find that soon. But we know two qualities from this very simple thermodynamics argument, that the voltage has to be proportional to the resistor, the power of the voltage has to be proportional to the value of the resistor, and has to be proportional to the absolute temperature. We can always actually say one more thing about this, which is quite interesting. Now, the question is that, can we say something about the power spectrum, the shape of the power spectrum, the frequency dependence of this thing? So think about it this way. If the power spectrum, if they are at the same temperature, so now let's go back again to the case where they are. So this is one part, this derivation. Now, if the temperatures, if you say that they are at the same temperature, T1 equals T2, then I argue that the spectrum of the power spectral density, of the distribution of the energy, so let's say Vn1 squared over delta F of omega, has to be related via a scalar property, scalar quantity, to the power spectral density of the other resistor. So I'm saying that their power spectral densities have to look the same. They have to have, except for maybe a proportionality difference. Right? I mean, they may be different to a constant, multiplicative constant. But they have to be the same. Now, why am I making this argument? How do we know that? So imagine, it's a proof by contradiction. Imagine that you have one of them, so this is Vn1 squared over delta F versus omega, and then this is Vn2 squared over delta F. Now imagine you have these two spectra that are not related through a scalar, right? If you have something like that, what you can do is that I can place a filter here. If I put a bandpass filter of this bandpass filter at this frequency, what would happen? So now what happens in this case is that one of them is providing more power than the other one, right? So you can actually get net power transfer from resistor 1 to resistor 2. Because now you can basically send, and this will be larger than that. And is that okay if they're at the same temperature? You're extracting work from two reservoirs that are at the same temperature. So again, you're violating the second law of thermodynamics. You may say, wait a second, but what if these power spectral densities are exactly on top of each other at this point? Sure, but then it means that if I put another filter here, then I can extract work by taking energy from resistor 2 to resistor 1. Right? So the only way that there would be no frequency at which, by narrowing down the bandwidth and putting a bandpass filter, I can get net work out of two resistors that are at the same temperature, would be that their spectra are proportional to each other at all frequencies, with this constant proportionality constant, right? Because otherwise, by putting these filters, I can extract work from something I shouldn't be able to extract work from. So that tells you that so it says that the two resistors, so what do we know from this thing? We know that the voltage spectrum of the voltage power spectral density is related to, proportional to the resistance. The voltage power spectral density is proportional to temperature, and at the same temperature, the spectra of the power looks the same, irrespective of other parameters. So the only thing that determines the spectrum of what comes out from the one resistor versus the other one, the spectrum of the power, is really its absolute temperature. So these are coming from basic thermodynamic arguments, right? So now we can actually try to make it a little bit more elaborate, and we can actually try to derive what the power spectrum looks like, now that we've done some basic thermodynamics argument. To do that, there are different ways of doing this. Again, well, we've picked a relatively simple, kind of like circuit hardware-oriented derivation. There are more elaborate, more kind of deeper derivations that you can do, but this derivation is actually due to Nyquist, and it's an interesting one. It's a good derivation. It's instructive. So it's the same setting. You have a resistor R1 and the noise source. Now, and you have resistor R2 and its associated noise source. But now, one of the things that you're doing, the way you're doing it is that you're connecting them, instead of being adjacent to each other, through a transmission line. So you have a transmission line. So you've attached this here and this there. Think about a coaxial cable or any kind of transmission line. It doesn't matter. And this transmission line has a length. And let's say each one of them has, so this is SV1 of omega or F, which is Vn1 squared over delta F. And this is SV2 of F, which we can show also as Vn2 squared over delta F. And let's say this transmission line has a length L. Okay, so it's a transmission line. And let's say these resistors are actually the same. Let's keep these resistors as R, the same R. Now, the other thing that we are thinking about is transmission line. Why are we using a transmission line? Because we want to have a finite, non-zero propagation time. We want to think about actually this propagation speed, the speed of light, if you will, propagating. So what is that speed of light? I mean, there would be some velocity, right, associated with this. You can say velocity is going to be 1 over, if it's a transmission line, it would be, for example, a classic transmission line, it would be 1 over LC, where L and C are the unit length inductance and unit length capacitance. That's and then it will have a characteristic impedance, and let's say it's matched, to make it simple, which basically means that we are making this assumption. Again, these are not fundamental to the derivation, how they're related to LC. I'm just giving you an example of what it is. So it's matched. So the question is that, what is the power that you will deliver, the power that's delivered to the transmission line at any point in time? So the power going from left to right, if you think about it, so what this means that the impedance looking into here is also R, right? If you think about it, you have a voltage source, you have a resistor R, and then you have a resistor R. And this voltage, if this voltage is V, this voltage is going to be what? V over 2, right? And if this voltage is V over 2, or V1 over 2, what is the power delivered here? What is the dP, the unit of power that's delivered at any, the power delivered is basically what? P is this voltage squared divided by R. So you get V1 squared over 4R. So that's the power that goes into the transmission line from left to right, that propagates through it and ends on the other resistor. So if you think about it, the power that's delivered, so this power is spread across various frequencies, right, in general. It would be a different frequency. So if you look at it, then if you have a power spectral density that's given like this, SV of F, then the power that's within a, so this is, let's write it down, power within a dF segment of the spectrum. So this is a part of the spectrum of this thing, which is dF wide. The power within that, we show it as dP, is going to be the power spectral density, which is basically this thing. So it would be 1 over 4R Vn squared over delta F times dF. or you can write this as also as S1 of f. This is the power spectral density of this source, which is what we're trying to find, right? So I'm saying that this power spectral density that we're trying to find times df and divided by 4r to get the actual physical power gives you the total physical power that is within that sliver of frequency, a df sliver of the spectrum. So if this is your spectrum that you're trying to find, so this is your SV1 of f, this is the power within a sliver df. So that's dp, this quantity, right? So now, how long does it take for this power that's going into this transmission line to end up here? What is that time? The time is simply the length divided by the velocity, right? The propagation velocity. So that time, t or tau, whatever, like call it tau, is going to be L divided by velocity. So this is the time it takes this power to just launch power at any point to get to the other side. Now, how much power is inside that transmission line at any point in that sliver of frequency if those two resistors are equal? This was just the power that goes from left to right, right? So this was left to right. If these two resistors are the same value, if they are the same value, then the same amount of power will be traveling from right to left at any point in time, right? So there would be twice as much. So the total power, the total energy that is inside that transmission line in that sliver of the frequency, dE, is going to be 2 times the time tau times dP, right? Because tau times dP, the time is basically defines the total energy that's inside here, because that's the net average power, times the time it takes to travel. So that's the total energy that's going from left to right. And then the same amount of energy that goes from right to left. So that's the total energy that's in that sliver, which you can basically show as, now you have to find the dP to this. So it's times this. So you can actually write this as so you can write it as, take this. And then basically what you get is 1 over 2r tau S1 of f df, right? So that's the power, that energy that's inside the transmission line within that sliver of frequencies, within that range of frequencies, that narrow range of frequency, df. So now let's imagine that we do following. So we'll go and at some point in time, so this is an interesting experiment, we short circuit the two ends of the transmission line. So we'll all of a sudden remove the resistor, just put a perfect conductor at the end of the transmission line. And let's say this is a lossless transmission line. How much energy gets trapped in there? Well, that much at each frequency, right? Because that energy was already there, it gets trapped in there. But now you have a transmission line that's shorted on both ends. So it can support only a finite number of modes, certain modes, right? You have a transmission line, you've shorted it, it has a certain amount of energy in it. The question is that what modes can it support? Right? You put energy into a lossless transmission line, you put perfect reflectors at the end, it goes back and forth, back and forth. You have to make standing waves, right? And what are those standing waves? What do they look like? So if you look at them, they're different modes. The first one looks like this. The second one looks like that. The third one looks like this, if this is the length. And so on and so forth, right? So what do you get? So you get all these modes that can be sustained. So what is the relationship between these modes and the length of the transmission line? We know that for each one of these modes, what should the length of the transmission line be in terms of the wavelength? It should be an integer multiple of half the wavelength, right, to form standing. So L has to be n times lambda over 2, right, at any value of this thing. Now, if you think about it, lambda is related to the velocity of propagation right? And the frequency. So I can express it in terms of frequency. I can write it as n velocity. This is the velocity divided by 2f. Okay? Now, f, therefore, is going to be what? Is going to be n divided by 2n times velocity divided by 2l. But what is this quantity? Velocity divided by length. It's 1 over the time that it takes it to travel from one end to the other, right? So we can write it in that form. We can write it as n over 2 tau. So what does this tell you? It shows you that frequencies that are supported are not any arbitrary frequency. They're spaced. So it says the supported modes are modes that are spaced 1 over 2 tau apart. Right? So the question is that how many of these modes can we support within a df? So if this is df, how many of these fall within the df? Let's just use a different color. So if this is df, how many of these modes fall within the df? Correct, 2 tau df, exactly, right? Why? Because what you get is that m, the number of supported modes, according to the simple calculation, is going to be df divided by the spacing of these guys, right? 1 over 2 tau, which would be 2 tau df, as you pointed out. So it's 2 tau df. Now, that's the number of modes that are supported. Now, there's one more thing. So these are the number of modes that are supported. That's fine. And then now we have the equipartition theorem. If you use the classic equipartition theorem, it says each one of these modes, what does the equipartition theorem say? It says each degree of freedom, right, in the system, each independent degree of freedom takes kT over 2 of energy. Now, there's a little subtlety here because there are 2 degrees of freedom for each one of these modes. You can think about it as a magnetic and electric, or you can think about them as 2 polarizations. So the actual degrees of freedom associated with these modes is twice as many. So you get that many. So you get basically the total. So the total energy in that bandwidth, dE, is going to be 2m, the number of degrees times that 2 degrees of freedom, times kT over 2, right? That's the number of degrees. That's an amount of energy, because each degree of they have these many degrees of freedom, and each one takes half kT. So that's what you get. Now you take this and plug it in. This cancels that, of course. So you get 2 tau kT df. So that's the total, the energy which is within that sliver, according to this. But we did calculate this quantity differently, right? We did calculate it like this too, the energy that was in there. So if you take these two and equate them, what would you get? You get 1 over 2r tau S1 of f equals 2 tau kT, and then there's a df, there's df, equals 2 kT df. So df cancels df, right? Tau cancels tau. And what you're left with is that S1 of f is 4 kT r, which is also Vn squared over delta f. So according to this calculation, the power spectral density of this resistor is a white noise with power spectrum of 4 kTr. So, which is consistent with our earlier conclusions, right? It is proportional to R, it's proportional to T, and the proportionality constant is 4K, where K is the Boltzmann constant. So that's all interesting and good. So what happens is that this is okay, but and it's coming from a thermodynamics argument, but it is predicting white noise, right? Which we argued earlier that would have infinite energy, therefore it can't be physical. So what is wrong? Well, this is an expression that we use a lot of times, and we'll see why we can use it a lot of times. We will assume that the resistor noise is white in many calculations, but it clearly cannot be exact. It cannot be accurate. It cannot go to infinity, because if it's white to infinity, then it has infinite energy, and that cannot be true, infinite power. Really. So what went wrong in this calculation? There was one assumption somewhere that broke down, really caused this. It actually goes back to the way we used equipartition theorem. Because equipartition theorem, the way we use it, assumes a Boltzmann distribution and assumes that your photon energy is not as large, is much smaller than the kT. If you're dealing with photon energies, h nus or hfs, that are much comparable to the kT, then you can't use the equipartition in that form. What you will need to use is that the more accurate expression is that, so if hf comparable to kT, then each degree of freedom, in fact, takes hf over 2 divided by e to the hf over kt minus 1. That comes from the Bose-Einstein distribution, because you're dealing with the photons, and you have to use the Bose-Einstein distribution, not the Boltzmann distribution. And if you use the Bose-Einstein distribution, this would be what each degree of freedom takes. And you can easily see, if hf is much smaller than kt, right, then you can write this as 1 plus x e to the x, right? It would be 1 plus hf over kt. So 1 cancels 1, you are left with hf over kt, and hf cancels hf, and then you get kt over 2. Right? So for that, then it becomes kt over 2. So now if we take this and plug it into this expression, where we use the equipartition theorem, which was, where was it? It was here, right? So if you use that instead, what would change? Let's find out. If you use that instead, then here, instead of this guy, you will have to get 2 tau hf over e to the hf over kt minus 1. Right? That kt becomes hf over kt minus 1. That divide by 2 and divide by 2 are having the same effect. So if you plug that in, then what you will end up here, instead of this expression, is you get 4ktr, but now instead of that, you have hf over kt divided by e to the hf over kt minus 1. So you can write it this way. So this would be a correction factor, if you will, to the white noise. Now, if you look at this and plot it, what you will see is that the original expression obviously is white, right? And so what it gives you versus frequency is that it's going to be flat. So this is the 4ktr. Now, this expression, if you look at it when f is small, reduces to 1. Right? Because what you get think about the Taylor expansion of e to the x. It's 1 plus x, right? So 1 cancels 1, you get x, you get hf over kt is 1. And as the frequency increases, at some point it starts becoming smaller. Because this becomes larger than 1, and it makes the denominator smaller. So it's not truly white. It is something that drops. And if you want to make an approximation of this thing, you can say, you can keep the first order term of that. So if you keep the first order term, what do you get? We're running out of space here. The first order term of this thing would be what? It would be, if you keep that, you get hf over kt. you get 1 plus hf over kt plus hf squared over kt squared over 1/2 minus 1. These guys cancel. One of the hf's cancel. So you get 1 over 1 plus 1/2 of hf over kt. So you have to really look at this quantity and say when it becomes important, at what frequencies, to see if it matters or not, right? So what we need to really calculate is essentially kt over h, because that would be a reference frequency for f, right? When f becomes comparable to that. So let's do an estimation of that. What is k? I mean, so since we are doing estimation, right, let's just keep the orders of magnitude, right? So k is 10 to the negative 23. It's 1.38, 10 to the 23, but just 10 to the 23 times 300. So let's say, okay, and that was like, so let's say at room temperature. So that's 10 to the 2, and then there's a 4 roughly because of whatever you get, and then h is a 6.6, or let's say 7 or 6, 7. 10 to the minus 34 in the SI system, in the SI unit, right? So this is joule seconds. This is joule seconds, and that's basically joules per Kelvin. And when you look at these, what do we get? So let's forget about these parts. So you get 10 to the 21 divided by 10 to the 34. So it's 34 minus 21. So it's 10 to the 13. So this is around 10 terahertz. So for you to have to worry about this effect, you need to be at room temperature, you need to be around 10 terahertz to worry about it. However, let's say you are at 4 Kelvin, right? Or 3 Kelvin, like liquid helium, like 4 Kelvin. It doesn't matter, that's 3 Kelvin. If you're at 3 Kelvin instead of 300 Kelvin, then this is going to be at 100 gigahertz. So then if you're doing some really high frequency millimeter wave stuff at cryogenic temperatures, then probably you have to think about this. Well, the good news about it is that it's less noise, not more noise. So if you design for 4 kT, you're not going to get worse what you design, what you expect, that you will probably get something slightly better. So that's one thing. But you can see that the spectrum is really not truly white. It is something that changes with frequency, but the way it drops, it affects the way we think about it. And for certain applications and certain ranges of frequency, it doesn't really matter. So we have this source. You can clearly see that there's this thermal noise that we've done the derivation, and we know that it's 4 kTr. Now, from a circuit standpoint, let's look at it from a circuit standpoint now a little bit more and see how it behaves. So if you think about it, if you have a resistor, R. Now, what this says is that you can actually think about it as a voltage source, a noise voltage source, V squared over delta F, we know it's squared over delta F, of 4 kTr. Now, also you can convert it to a Norton equivalent, right? This is a Thevenin equivalent. You can have a Norton equivalent of this thing, which basically means that you can have a current source, noise current source, in parallel with your resistor. So you can say I have my resistor R, or R1 or R, and then I have a noise source. Now, the current noise sources I like to show them like this, to emphasize that they don't have any real direction because it's just random noise, right? So they're going in both directions. So that if you see that symbol, for voltage source, there's already things are symmetrical. So if you do that and you can compare it, you can easily see that then the I squared over delta F is going to be 4 kT over R, which you can also write as 4 kTg, the conductance. Right? So the current noise, there's an equivalent parallel current thermal noise, or a series voltage source. You can do it as either one. Now, one question is that you have to keep in mind, if you see a resistor in your circuits, which resistors generate noise and which ones don't? You have to think about this. For example, when we do small signal models, right, you can have an RM or an R pi. do they generate noise? Do you have a noise for R pi necessarily, or Rm? A thermal noise associated with them? Not necessarily, because they are not necessarily dissipative resistors. They are incremental resistors. They are derivatives. They are slopes of curves. So again, the measure is the fluctuation-dissipation theorem. See what dissipates? Real energy. That's what generates real thermal noise. There are other kinds of noise sources that we'll talk later about next. But as far as the thermal noise is concerned, you need to really have true loss in the circuit. Now, let's see if this model actually makes sense. I mean, right, we can do a couple of different things about it. For example, you can say, what if, is this consistent? You can say, well, wait a second, let me see. If I have two resistors, R1 and R2, what happens? Well, if you have two resistors, R1 and R2, in parallel, each one of them has its own noise source, right? So let's call it IN1 squared over delta F. And then you have R2 with IN2 squared over delta F. So how should I add these two noise sources if they're two resistors? Because think about it. We said when you're adding noise sources, when we're talking about the mathematics of it, we have to know about we have to think about the correlation, how they are related to each other, right? So do you think, how should we add them? Should I add them in amplitude? Do you think they would be correlated, uncorrelated, partially correlated? What do we think? Two resistors in parallel. How is this noise generated? Think about that. Is there thermal fluctuations of charge carriers, possibly electrons or maybe holes, inside this resistor, right? And this resistor. Do they have a way of directly affecting each other? This like localized? No, they're independent. So they would be uncorrelated. And as such, they would add in what? In power. So what you need to do is just you can say, well, the overall effective equivalent noise power of this thing, of the parallel resistor, is going to be the sum of the two powers, IN1 squared over delta F plus IN2 squared over delta F. Now, what was IN1 squared over delta F? So from this, we saw that it's 4 kT over R, right? So it's 4 kT over R1. And this is 4 kT over R2, which basically gives you 4 kT, 1 over R1 plus 1 over R2, which is another way of saying 4 kT over R1 parallel R2, which you can see is consistent now, because now you have a new resistor of this value, which is producing a noise consistent with this expression, which is another way to say that it proves that these two noises have to be uncorrelated, because they're generated independently, right? So that's one thing. There's a couple of other interesting things about KT over the thermal noise. One of them is what happens if you have some capacitance in the circuit. And this is very interesting because it has many interesting implications in terms of design. And it's a very simple way of thinking about many different situations involving noise. So imagine that you have a resistor R in parallel with a capacitor C. And of course, this resistor now has a noise source, thermal noise source or Johnson noise source, which is 4 kT over R, right? So this is IN squared over delta F, similar to here. Now you have a capacitor in parallel. The question is, what is the voltage noise that you will get here? Well, we know how to calculate this, right? Because we have that expression that relates the power spectral density of the input and output in an LTI system. If you know the transfer function, it's the transfer function magnitude squared times the input that gives you the output. So the transfer function between this current and this voltage is the impedance, right? So that impedance, which is basically V out over I in, which is the impedance, is R over 1 plus RCS. So as a function of frequency, you can write it as, or like the F, so you can write it 2 pi RCF. That's the impedance. So the magnitude square of this thing, this magnitude squared is clearly R squared over 1 plus 2 pi RCF squared. And now you plug this noise source in, so we say Vn squared over delta F, the output noise spectrum, voltage noise spectrum, is the input current spectrum times this transfer function magnitude squared, which if you plug in the values, you get 4 kT over R times R squared over 1 plus 2 pi RCF squared. So it looks like a bandpass response, right? So the voltage noise will have a power spectral density that looks like this. But the question is, how much power is there total in this voltage? Is it finite? Is it infinite? How much is it? Well, to find out what the total power is, or essentially the voltage average voltage power, I guess, like the mean squared average of the voltage, you need to integrate. We know that we need to integrate from 0 to infinity. We need to integrate the power spectral density, right? Which is this thing, this quantity. So if you integrate, so the question is that what is the integral of this thing? So by the way, one of these r's cancels. So it's basically the integral from 0 to infinity of 4 kT integral from 0 to infinity of df over 1 over 2 pi RCF squared. So it's this integral from 0 to infinity. Well, to do this integral, we need to do a change of variable, right? We can define this as u, and then multiply and divide by 2 pi RC. We already have the r, so we need to divide by 2 pi c. So v squared, magnitude mean squared, is going to be 2 kT divided by pi c, integral from 0 to infinity of du 1 plus u squared. Does anyone remember what this integral is? Integral of the indefinite integral du over 1 plus u squared? No, it's simpler than that. It's inverse tan. It's tan inverse, right? So it's a tan inverse. So basically, it is 2 kT pi c tan inverse of u from 0 to infinity. So what is tan inverse of infinity? Pi over 2. And what's tan inverse of 0 is 0. So this is pi over 2. This is pi over 2. So pi over 2 cancels 2 over pi, so you get kT over c. So v squared is kT over c. This is actually so prominent that it's actually called kT over c noise. People call it kT over c noise. The most interesting thing to notice about this thing is that, first of all, it's independent of R. It doesn't matter what resistor you have. The voltage power that you will get, or the mean squared voltage that you will get across a capacitor, when you have a capacitor involved, from any resistor, is really inversely proportional to the capacitor. It's kT over c. It has no dependence on R. Now, there was a much easier and much more physical way of arriving at this result. Much more kind of like logical and intuitive way to arrive at this. But I wanted you guys to see this first. You see, so what does equipartition theorem say? It says each degree of freedom in thermal equilibrium takes 1/2 kT of energy, right? What is the energy of a capacitor? What is the energy? So how many degrees of freedom do we have in here in the circuit? We've talked about these things when we're talking about degrees of freedom, order of the circuit, poles, things of that sort, right? 1. You can define one initial condition, right? So it's 1/2. Do you agree that it's 1/2 CV squared? The energy inside the capacitor? So now what does equipartition theorem tell us? This is equal to 1/2 kT. So V squared is going to be kT over c. So by this argument, by the way, you can say if I gave you an inductor and a resistor, and any kind of resistor, doesn't matter what resistance you have, then what do you get? The current is going to be, so the energy inside an inductor is going to be 1/2 Li squared, right? So then there's the I, for an inductor, you have an I squared, which would be kT over L. Right? It's not even limited to electrical circuit. If you have a mass sitting on the top of a cantilever, and it's a small mass, what's the energy? What's the kinetic energy of it? 1/2 mv squared, v being velocity this way, right? This time, velocity. If this is fluctuated by thermal stuff, you get basically that being 1/2 kT, so you get v squared. Now the velocity, mean square, of the fluctuations of a little kind of like tiny mass on sitting somewhere is going to be what? kT over m. This happens in small MEMS and NEMS devices. There's fluctuations because of the thermal fluctuation. So once you understand what equipartition theorem means, you can apply it in many different ways, some of which are electrical. So that is an interesting, that's an important thing, kT over c, because this kind of noise actually is what determines, for example, how big or how fast, for example, a sample and hold or an A to D can work. Because if you think about it, if you have an A to D or a sample and hold you're trying to sample, you have a switch and a capacitor, right, that you're charging and discharging. So to make it fast, what do you need? We know the basic trade-off, right? If you want to make something fast, either make it light or you drive it with a lot of force. Meaning either you lower the capacitance or you increase your drive capability, which means that either you make it lower capacitance or burn more current. So you want small capacitors, right? Ideally. You want to make your sample and hold capacitance as small as possible. Or if you're making a switching A to D or something like that, switch capacitor A to D, you want to make the capacitance as small as possible. But the lower end is determined by this, because the smaller you make it, the more noise you get. So depending on what size of LSB you're trying to resolve, then you may not be able to go below a certain minimum capacitance. So that's an important thing. Now there's one more interesting side note that I'd like to actually introduce to you. Let's see what we have here. Yeah, I think we can erase this stuff. And that's the question of, we said that the noise of the resistor is not really white, right? So it must be finite. It's not infinite, the noise power coming out of it. And we said that, okay, if you use the Bose-Einstein distribution, you will get this expression, right? That we did the derivation for here, right? This expression. So one question is, how much energy is there in the resistor? Can we calculate what that is? So what is the total power, more accurately, what's the total available power? What is the available power of a resistor due to thermal noise? So to do that, we need to really integrate from 0 to infinity Vn squared over delta F divided by 1 over R dF, right? You have to integrate that. Now, of course, if you put 4 kT in there, you will get nothing, right? Because you will get infinity. I mean, you will not get nothing. You will get something that's not clearly correct. So we need to use that expression. So if you do that, you get a 4 kTr divided by R. So R cancels. Then you get integral from 0 to infinity of you get hf over kT divided by e to the hf over kT minus 1. Now you can define this as u. So this becomes 4 kT integral from 0 to infinity of this is df, u du e to the u minus 1. Right? Now this integral actually has a closed form solution. And we are not going to do that. I mean, you can do the residues and all those things to calculate it. But it's basically pi squared over 6. So what you get, now the only problem, oh, okay, so there's a problem here, by the way. This is not exactly correct the way I wrote it. Because the df needs to be made into du, right? So I need to multiply and divide by kt over hf. So I need to multiply this by h over kt, and then divide by, or get kt over h here to get du. So then it becomes 4k squared, kt squared, let's say, divided by h, then integral from 0 to infinity of u du over e to the u minus 1. Yep. And I have a, something like that. Just check something quick. I think I made a little mistake somewhere. No, it actually is correct. Good. So this thing, this integral is pi squared over 6. So you get 4 pi squared over 6, bunch of constants, kt squared over h. So this is a quantity you can calculate, right? And obviously it depends on the temperature, and the temperature only, right? So if you just purely use the temperature to calculate this thing, you can actually, if you simplify this quantity, it becomes, so at room temperature, for example, at T equals 300 Kelvin, what do you think the total noise power of a resistor is? So this is the total noise power that the resistor has, the thermal noise power. All of it from 0 to infinity at all frequencies. How much do you think it is? And you can see it's not related to R. Right? What do you think it is? Just take a guess, number-wise. Picowatts, so that's one guess, okay? What is it? What do you think? Any other guesses? Yeah, it's going to be pretty small, right? But also you have h in the denominator, right? So yeah. But it's 40-something nanowatts. So next time somebody proposes a scheme to generate energy out of like extracting thermal energy from this thing, other than like second law issues that you need to consider, but even if you got around them, you have to think about how much energy there is in each one of these resistors. So this is the total there is at room temperature. And of course, at lower temperatures, this is available power, right? So that's different. Now, and then you can use that to think of it as some sort of a minimum capacity, because this is some sort of, you can think about it as some sort of a kT over C, right? You can say, what is the equivalent kT over C noise associated with it? So if I say kT over C is equal to that quantity, like 4 pi, I don't think pi is squared here. I don't know why I got pi squared here. 4 pi, oh no, it is pi squared actually, sorry. That was correct, because the integral is pi squared. 4 pi squared over 6 times kt squared over h. So one of these kt's cancel, so you can write a c that's basically 6 over 4 pi squared h over kt. So this is, it's as if you remember kt over c, when you had a capacitor, if you had any capacitor, it appeared like there is some sort of a band limiting effect. So this, what we are trying to calculate is that the intrinsic limited power of the noise, or the fact that it's not white, what capacitance does it correspond to? Because what that means is that it's basically, and then you have to, and then you have to also balance for the R, right? So you have to make basically just, so because what you, okay, so we have to be careful. So we can't just set it. This is the total power, right? If you have to do a resistive power, right? So this is the actual power in the thing. But kT over C, remember, this was just the voltage squared. So we have to multiply it by R. right, to get. So there should be an R here as well, which basically means that there would be an R in the denominator here to convert it to a, because this is a voltage squared kind of thing. Okay, so it says that for a given resistor at a given temperature, there's a capacitance that is equivalent of what you can have. So having a capacitance below that is meaningless, because you will be dominated by this noise. So this is the equivalent capacitance of that. So you can basically say, R, if you have an R, a couple of numerical examples, R of 1 kilo ohm and a temperature of 300 Kelvin, at those levels, you have a capacitance that's 24 attofarads. So this is a pretty small capacitor, right? So it means that if you are at 24, below 20, I mean, there's an intrinsic capacitance of 24 attofarads for a resistor of 1 kilo ohm at 300 Kelvin. So it's as if you have an equivalent of that much in terms of noise limit, bandwidth limit is. Calculation is concerned. But now, if you think about it, for a 1 ohm resistor and the same room temperature calculation, then the capacitance becomes 24 femtofarads, which can start being something that's in the realm of capacitances that we consider. And then if you're at R1 of 1 ohm and the temperature of 3 Kelvin, this becomes obviously 24 picofarads. So this can matter. The total available noise in a system can have an impact in the analysis that we do and the way we think about the system. So we cannot be completely oblivious to that evaluation and assessment. Okay? Any questions? All right, that's it then.